Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I am going to be talking about how to find the equilibrium concentrations of a reaction when you're only given the initial conditions of the reaction. And at this point, what we're going to add to this particular example problem is a simplifying approximation that will make the problem easier. But then you have to double check to make sure that that approximation holds true, that is valid. So, and then we're going to apply what is called the 5% rule. Okay, so here's the problem that we're given. And so we are given that this reaction here, this balanced equation, and we're given that H2S is 0.0125 moles of this substance. And we're also told that this is in a reaction vessel of 0.5 liters. So 0.5 liters. Okay. So let's see, I'll write it up. I guess I'll write it up here. 0.500 liters is the reaction vessel that this reaction is taking place in. So the first thing we need to do is we need to figure out what the concentration is. So we can't just deal with moles, we have to have the concentration because that's what we're measuring. So we're looking for equilibrium concentrations. So these are going to be 0 here. So we don't have any reactant yet. And so, first thing we need to do is find the concentration. Well, we know the moles, we have liters, so we're going to divide this by the volume. So moles per liter will be the concentration of the gas. So if we take 0.0125 and divide that by 0.5, then what we get is same as multiplying by 2. This then becomes 0.0250 concentration. So we'll say moles per liter. So moles per liter. So there's our concentration that we begin with. And so now we have, and this is 0 concentration. And so these are our initial concentrations. So we're going to do our ice chart. So there's our initial concentrations. We're going to figure out the change, and then we have to figure out the equilibrium. Okay. So just by looking at this, we know that Q is going to be 0 because Q is going to be the concentrations of these two, right? Over, so concentration of H2 multiplied by the concentration of S2 over concentration of H2S squared, right? So you would put these values into here, but these are 0, so that's going to be 0. So Q is 0, so, and compare Q to our equilibrium constant. And if Q is less than their equilibrium constant, then that tells us that we have we have too much reactant and we need more product. So that's obvious from the fact that we are starting with 0 product. So we know that it's going to go towards product. But just so that you know, if Q is less than C, then you're going to have to need more product. That means you're going towards the product direction. And again, that comes from the fact that you're looking at a ratio here. So if this bottom part is too large, then it's going to cause Q to be small. So we have too much reactant, not enough product. So in order to get Q to go towards K, we need to decrease reactant, increase product. And again, that's obvious from the fact that we have 0 product. Okay, so we know we're going in this direction because we need to form product. So that means that our change in our concentration is going to be negative here, and be positive here. So we're going to have, oh, I forgot there's a 2 here, so that should be squared. My bad. So this should be concentration squared because there's a 2 there. There's a 1 here, so that's raised to the 1 power. So the change for here, if we're doing our stoichiometry, if this is gaining a certain amount, we're going to call that x. So here we'll call the gain in S2, we'll call that positive x. There's a 1 to 2 ratio between these two. So whatever is gained here in x is going to be gained as 2x here. And then the change here is a loss. So that's going to be minus, so a losing reactant. And again, because of the coefficient, it's going to be a 2 to 2 ratio here. So 1 to 2 here. So it's x here, so it's minus 2x there. Okay, so now all we need to do is add our initial conditions, or initial concentrations with our change, and we'll get the equilibrium concentrations. So this is 0.0250 minus 2x. This is just 2x plus 2x, and this is plus x. And so here we have the equilibrium amounts expressed in terms of x. Now all we need to do is find x. And that's where our expression for Kc is going to come in. So now we're going to write our expression for Kc. So Kc is equal to, again, just like Q, it's going to be the concentration of H2 squared multiplied by the concentration of S2 to the 1 power all over the concentration of H2S squared. Okay, so now we have our expression. Now all we need to do is plug in our expressions in terms of x, our equilibrium concentrations in terms of x. So H2 squared, that's going to be 2x squared multiplied by the concentration of S2, which is x. So we have x, and that's going to be divided by the concentration of H2S, which is this here. So, and that's going to be squared, so that's going to be 0.0250 minus 2x, and all of this is squared. Okay, so now we have our expression of Kc in terms of x, and again, this is going to be equal to that value there. So this is equal to 1.67 times 10 to the negative 7. So now we have our full expression. So at this point, all we need to do is find x, and we'll solve this. Yeah, sorry about that. Okay, so this looks like a beast to solve because we're going to multiply these two. This is going to be an ugly quadratic here. We're going to have x squared here. So this is, you're going to need a quadratic formula. So this is going to be relatively hard to solve. But we can use a trick called a simplifying approximation. And we can assume, or we could say, okay, this x value here, if x is really, really small, then the difference between these two is going to be negligible. And so if that's the case, then subtracting 2x from this is not really going to change this very much, assuming that the change is small enough, right? So that's the assumption we might make. So say, okay, this is too small. So we can just drop it and say, okay, we'll assume this is too small, and then basically we're left with this value here squared. And that automatically will simplify this really really quickly. So then what happens is we're going to get a cubed x here. So then this becomes, I'm going to write it over here, this becomes 4x cubed over 0.03, 250 squared, and that's going to be equal to 1.67 times 10 to the negative 7. So that becomes a lot easier to solve. So all we need to do is square this number, multiply by both sides of this number, divide by 4, and then take the cube root, and you've got your x. So let's go ahead and do that. So when you do that, x becomes 2.97. So here, x is equal to 2.97 times 10 to the negative 4. Okay, so here is our x value. And so what you want to do at this point is you want to validate whether or not that assumption was true. We assumed that x was too small, but now we need to validate that, because if it wasn't too small, then that approximation would not be valid. So we need to use what is called the 5% rule. And all you're going to do there is you're going to take x and you're going to divide x by the original concentration and multiply by 100. And so if it's less than 5%, if this x is less than 5% of the original concentration, then it was a valid assumption to make. So if we do that, so if we take x, right, divide it by 0.0250, multiply that by 100, and we get 1.19%. And so this is less than 5%, so that was valid. So that was a valid assumption to make. So at that point, we validated the x value. So now all we need to do, this x value here, now all we need to do is plug this in for x and then solve for the equilibrium concentrations. And when we do that, so we plug x in here, this becomes, let's see, 0.0244 for H2S at equilibrium, and then the other two, H2 becomes 5.94, so this becomes 5.94 times 10 to the negative 4. Let me double check that again. 5.94 times 10 to the negative 4. And then you have 2.97. And then this becomes 2.97 times 10 to the negative 4, because x is here. So that is how you go about finding the equilibrium concentrations, and that's how you use the too small approximation. So we might assume that we can make that too small, and then eliminate it, simplify our calculation, find x, but then we need to double check to make sure that our approximation and assumption is true. So we use the 5% rule, divide our x by the original concentration, or if we have pressure, you're going to divide it by the pressure, multiply by 100, and see if it falls below 5%. I hope this is helpful. If you like this video, like, share, subscribe, hit the notification bell, and thank you for joining me. I'll see you next time.